start the recording, and then I'll continue sharing. So what I have here is problem 4, and it's problem 4 from, let me just show you the start of this. It's from the May exam in 2017, and I'll go through problem 4 here. And let's see, what have we? We have a surface of revolution, and you see you have, say, an area or a region in the xz plane with this parametric representation. So this is given in the text. And this corresponds, if I could show you this on the figure, it's this part of or this surface here. And then you rotate this through the angle pi half, and by doing this, get you get a solid of revolution, and the first question here is give a parametric representation of sigma. So let's try to do this. And I write here, I have that we're given this parametric representation, u0 and v times cosine, no, times sine of u. So the question is a parametric representation for omega. So remember, when we do this, you need to rotate your figure in the xz plane. Let me just try to sketch it. Have here x, y, and z. And you have here, I should write the parameters. U belongs to 0, pi half, and v belongs to 0, 1. But and if you draw this in, it's just a sine curve as a boundary. That is, if you have u is varying between 0 and pi half, and v is varying between 0 and 1. That is, for any u, you have that the top point here is sine of u, and v indicates any point along this line. So you have this figure which you then rotate around the z-axis. And if we call the angle of rotation for w, then you know that w is in the interval from 0 to 4th. So this is the thing that I'm gonna use here. So the end, the stop, or omega equal to pi 4th, is along this line. But if I call, remember this will be of the solid, it will be a function, or it will be a parametric representation with 3 parameters. We have our u and v that describes the plane in, or describes the surface, so to speak, in the xz plane, and then I should multiply by this rotation matrix, cosine w minus sine w, and then sine w, cosine w, and then 0, 0, 0, 0, 1. And then I should use S in the xz plane, and this will be u 0, and then v sine. This will give me the parametric representation in the xz plane. So when you multiply this in, you get u times the first column, u cosine w, and then u sine w, and then for the third coordinate you only get the last part here. So this will be the parametric representation, and you see u is still between 0 and pi half. V is in the interval from 0 to 1. And then W is in the interval from 0 to pi 4th. What we are, well, let's go back to see the next one we're going to look at is determine the flux of V through the surface of omega. So if you count the different surfaces of omega, then you have 3 vertical surfaces. One is curved, and the other 2 are plane, and then you have the top and the bottom. In total 5 surfaces, so you have to, if you want to compute the total flux, you have to compute 5 different flux integrals. And I think we can do better. And we can do better because we can use the Gauss, or Gauss's theorem. Because then we only need to do a volume integral of the divergence of the field. Let's try to do this. So I'm at 2 now, and I should, right here, we are using Gauss. When we're using Gauss, we need to compute the divergence of our vector field. And let me just go back. I don't think I have included the vector field yet from So let me just go back here. You see the vector field is given here. So it is x squared minus 2yx and then comma z. So I write here v is x squared minus 2yx and then finally z. I need to compute the divergence of this vector field here. So it will be 2x, and then I should differentiate the second coordinate with respect to y. I get minus 2x, and then finally z with respect to z, that is plus 1. So the divergence is 1. Now it becomes truly easy because when I calculate the flux through the surface, it is this one I have here times n. So this is the flux through the surface, and this is equal to the volume integral of the divergence of the vector field. And since the divergence is 1, you get 1 times this integral here, and this is simply the volume of your solid field. So we need to determine the volume, and you see omega is now it's a solid of revolution. There's no easy formula. It's not a cylinder. It's not a pyramid or a cone or anything like that. So you cannot say, look up the volume of this. You have to compute it. And you compute it by computing the Jacobian function, because this is simply say the integral of, no, let me wait with this. Let me just compute the Jacobian. And the Jacobian I get from the determinant of this matrix. This is R prime U, R prime V, R prime W, where these are the columns of this matrix here. So this will be the determinant. Let me see, we have say the parametric representation. So if we compute the derivative with respect to u, you can see you get cosine w, sine w, and then the derivative of the third one is v times cosine u. Let's write this down here. So you get cosine w, sine w, and then v times cosine u. This was the first column. The second column, if you go back, you see that only the third coordinate depends on v. So when you differentiate, you get 0 on the first two parts. 0, 0, and then you get sine of u. Finally, when you take the derivative with respect to w, you get 0 for the third part, doesn't depend on w, but for the first two coordinates, you get u minus sine w, minus sine w, and then you get u cosine w, and then you get 0. So this is three columns of this matrix, and then you just have to evaluate this. And of course, if you have a Maple open, you can do it by Maple. But in this, this you can easily solve because you see there is a column here with two zeros. And so you get, then you should, I choose this one, and then you should calculate the sign. So it's plus, minus, plus, minus. So you have a minus, you have minus sine of u, and then I need the determinant of this submatrix, so I need to compute this times this minus this times this, and this will be u. This will be u times cosine squared w, then plus u times sine squared w. So the result is minus u, see this is equal to u, sine of u. But remember now that the Jacobi is equal to the numerical value of this, minus u sine u. And since u is between 0 and pi half, sine is not negative, and so this will be equal to u sine u. And now you're ready to find this this integral. You have that flux is then equal to the integral from 0 to pi fourth, that was w, and integral from 0 to 1, that was the integral in v, and then finally this integral from 0 to pi half, that was the integral in u. And the integrand is a Jacobi function. Sine u du v dw. And you can fairly easily calculate this integral. You can see that you have to use partial integration in order to do the integral with respect to u. But you will have been able to do this. The result is that this flux here is pi fourth. Now let's look at the final the final problem here. I just delete this. And let's look at them. Here you are looking at a surface G. And G is the part of omega that bounds omega above. And it's blue in the figure. I could point to that part of the figure like this. So this is the part. And we should determine the circulation of V along the boundary of G when the boundary curve is oriented as indicated by the arrow in the figure. That is, you are, say, if you're going in this direction around the curve, as seen from top of the z-axis, you're going in the counterclockwise direction. So, and again, if you look at the three different parts of G, that is this one, this one, and this one, then you need to compute three different integrals in order to do that. And I think we can do better by using Stokes. So let's try to do this. So this will be Q3, and we need a parametric representation for G. But this is fairly easy to get this, because if you go back and look at the parametric representation for omega, then you can see that if you put V equal to 1, then you are on top of, I have shown it here on the figure. Let me just mark this for you here. So when V is equal to 1, you are at the top of the solid of revolution. And so you can simply get the parametric representation for G by putting V equal to 1. And here, so you just put V in equal to 1 here in the parametric representation for R. So let's do that. Let me call it, I can call it for S. And it's now a function of only two parameters, because it's a surface, and it is equal to R, U, and you have put V equal to 1, and then W. So it is equal to U cosine W, U sine W, and then sine of U. And U is, that was wrong, it's pi half, and W is still in the interval from 0 to pi fourth. In order to do this integral, we need to compute the curl of the vector field. That is, we need to compute dx, dy, dy and dz. The cross product of this and the vector field, which was x squared minus 2xy and then z. If you take, you have to take, let me just point to this, this times this minus this times this, and you see this doesn't depend on y and this doesn't depend on z, so you get a 0 in the first part, and in the second part you have a 0, and then finally you get the third coordinate, and here you get minus 2y. So now we can compute this circulation along the boundary as the flux integral of the curl of the vector field times a normal vector to G. So in order to apply this formula, we need to compute the normal vector to the surface. And actually, this is a unit vector. And remember, when you do the flux integral, you need to compute capital N. So I'm going to do this now. I'm going to compute it as with my parametric representation. I think I have now used S. Yeah, S to denote this. So it will be S prime U cross S prime W, and S, it will be, if you look at it, when you differentiate this with respect to U, you get cosine W, sine W, and then cosine U. So this will be this tangent vector here, and then you should cross it with, when you differentiate with respect to W, for the first coordinate, you get minus U sine W. So minus U sine W, and then you get U cosine W, and then you get a 0 because the third coordinate doesn't depend on W. And then you need to evaluate this. You get minus U cosine U cosine W minus U cosine U sine W, and then you get U. Now, what we need to verify is that this is pointing in the right direction. So let me just take this normal vector at the point pi fourth, comma pi fourth. That is in the middle of G. So I get minus pi fourth, and then cosine of pi fourth is 1/2. Cosine of pi fourth is 1/2. And similarly for the second coordinate, I get minus pi fourth. And then again, 1/2. No, sorry. Let's look at it. I just take this away because you see cosine of pi fourth is square root 2/2. And similarly for cosine of w, which is pi fourth, square root 2/2. And here you also get, and then finally you just get pi fourth for the third coordinate. So it'll be minus pi a minus pi a, and then pi fourth. So you see the x component is pointing in the negative direction. The y component is pointing in the negative direction, but the third or the z component is pointing in the positive direction. So if you look at, I can just show you this. If you look at this, and then you are in the middle of this figure and it's pointing in this direction. So the right-hand side is fulfilled for this. I write here, NG is directed so it fulfills the right-hand rule. I should write in relation to the boundary dg. And now we can compute the integral. We have the integral, this circulation along the boundary in this way. And then we use Stokes theorem. And then we compute the integral as, I should say here, as the integral from 0 to pi fourth, and then the integral from 0 to pi half, that is u and that is w. And it will be the dot product between the curl of v restricted to the curl of v restricted to the parametric representation. So if I look here, this is the curl of v. So here I have to put in y from the parametric representation, and you see y is given like u sine w. So this is what I'm going to do. So I get 0, 0, and then minus 2u sine w. This was the curve, and I have to dot this with the parametric representation. or with the normal vector here. And so I simply write down this normal vector. It would be minus u cosine w minus u cosine u sine w, and then u. And I need to integrate with respect to du and dw. So this will be the integral from 0 to pi fourth and from 0 to pi half of, there's only contributions from the third coordinates in this dot product, so it'll be minus 2u squared sine w, and then du dw. Not very nice. W. And when you compute this, you get the result square root of 2 halves minus 1. This is the W integral. And then you can compute the other one that will be minus, or it'll be 2/3 of this, and it'll be pi third 12th. So this is the solution. This is simply the flux. So this was simply the last lesson in Math 1 this spring term, and it has been a pleasure being the teacher for you this past year, and I wish you all well at the exam, which will be a bit special. You can join my lecture or my, at 3:30, I will answer questions about homework 7, and this will give you some indication on how the exam will be. But I thank you for my part and wish you well with the exam and with your future study at the Technical University. Thank you very much.